What if there were places in the universe where time itself begins to fail, not slow down, not stretch, but break from everything we experience here on Earth, because time feels constant, reliable, predictable. 1 second follows another. Cause leads to effect. The past stays behind us. But beyond our planet, beyond even our solar system, there are regions of space where that certainty disappears. And if we were to approach one of those places, something extraordinary would happen. Clocks would disagree, light would bend, and reality would behave in ways that challenge our deepest assumptions. By the end of this journey, you'll understand where time bends the most, where it nearly stops, and where physics itself reaches its limits. If you enjoy exploring real space mysteries grounded in science, you might like where this story leads, because the most dangerous place in the universe isn't defined by heat or radiation. It's defined by time, and it begins with a simple idea. Gravity doesn't just pull on matter, it pulls on time itself. Here on Earth, gravity is gentle. It keeps our feet on the ground. It keeps the moon in orbit. But according to Einstein's theory of general relativity, gravity is not just a force, it is the curvature of spacetime. Mass bends the fabric of the universe, and time flows along that curve, which means time does not pass at the same rate everywhere, even here. Clocks at higher elevations tick slightly faster than clocks at sea level. GPS satellites must correct for this difference every single day. Time already bends. But what happens when gravity becomes extreme? What happens when space-time curves so sharply that time nearly comes to a halt? That's where we begin to approach the most extreme environments in existence. But that's only the first layer of this story, because gravity is just one way time can stretch. There are others, and the first true place where time begins to break lies at the edge of something far more powerful than a star, a place where escape becomes impossible, a place called a black hole, and this is where things start to become deeply strange. The edge of a black hole. Imagine standing near the edge of a black hole, not falling in, just hovering close enough to feel its influence. From your perspective, your clock ticks normally. Your heartbeat remains steady, but to someone far away, watching you from a safe distance, you begin to slow down. Your movements stretch. Your voice lowers in pitch. Your seconds expand. This is gravitational time dilation. The stronger the gravity, the slower time flows relative to distant observers. And near a black hole, gravity becomes so extreme that time nearly freezes. The boundary of no return is called the event horizon. Cross it, and nothing, not even light, can escape. But something remarkable happens just outside that boundary. To a distant observer, anything falling toward a black hole appears to slow infinitely as it approaches the event horizon. It never quite crosses. It fades, redshifts, disappears. From their perspective, time has nearly stopped. But from the falling object's perspective, time flows normally. It crosses the horizon without noticing anything unusual at that exact moment. Two observers, two completely different experiences of time, and both are correct. This is not science fiction. It is a confirmed prediction of general relativity, but that's not the strangest part, because at the center of a black hole lies something even more extreme, a singularity, a point where our current understanding of physics breaks down. Density approaches infinity, space-time curvature becomes infinite, and equations that describe the universe everywhere else simply stop working. We don't yet know what truly happens there, but many physicists suspect that this is where time, as we understand it, ends completely, not slows, not stretches, ends. And yet, black holes may not be the only places where time behaves this way. There is something even larger, even more powerful, at the heart of almost every galaxy, including ours, Sagittarius, a star, the giant at our center. At the center of the Milky Way lies Sagittarius, a star, a supermassive black hole with a mass about 4 million times that of our Sun. Stars orbit it at incredible speeds, Gas spirals inward, heating to millions of degrees. But what makes Sagittarius a star extraordinary isn't just its mass. It's the way it reshapes time around it. Astronomers have observed stars orbiting dangerously close to this black hole. One star, known as S2, swings around Sagittarius A star every 16 years. At its closest approach, it moves at nearly 3% the speed of light. And during that close pass, something measurable happens. Time slows. Not dramatically, but detectably. Einstein's equations predict exactly how much time dilation should occur, and observations confirm it. Which means near supermassive black holes, time doesn't just theoretically slow, it measurably does. But what scientists discovered next changed everything. Because if gravity can slow time, velocity can too. And there are places in the universe where objects move so fast that time stretches for a completely different reason. Near the speed of light, time behaves in ways that challenge intuition. And this leads us to a region of space where matter itself is accelerated to almost unimaginable speeds. A place powered by spinning black holes. A place where time stretches along beams of pure energy. Relativistic jets. Time at near-light speed. Some black holes spin, and when they do, they can launch jets of particles thousands of light-years into space. These are called relativistic jets. Inside these jets, particles move at speeds close to light itself, and according to special relativity, the faster you move, the slower time passes for you relative to others. This is velocity-based time dilation. If you could ride inside one of those jets, moving at 99.9% the speed of light, your clock would tick dramatically slower than clocks on Earth. Years for you could mean centuries elsewhere. But here's where it becomes even more interesting. Some of these jets are pointed directly at us. We call them blazars. Because of relativistic effects, their light appears amplified and distorted. Time itself appears compressed from our viewpoint. Events seem to happen faster than they physically should. Reality depends on motion, and motion reshapes time. But even this is not the most extreme example, because there are theoretical objects even denser than black holes, not larger, but stranger, objects that may not exist, but could. And if they do, time near them may behave in ways we cannot yet fully describe. Neutron stars, the edge of matter. When massive stars explode, they can leave behind neutron stars. These objects pack more mass than our sun into a sphere only about 12 miles across. Their gravity is immense. Their magnetic fields are trillions of times stronger than Earth's. On the surface of a neutron star, gravity is so intense that time noticeably slows compared to distant observers. If you stood there, hypothetically, time would pass slower for you. But neutron stars introduce another phenomenon. Extreme density pushes matter into states we cannot recreate on Earth. Atomic structures collapse. Electrons merge with protons. Matter becomes neutron-dominated. And inside that environment, quantum physics and gravity interact in ways we do not fully understand. What scientists discovered next changed everything. Because there may be even stranger objects, hypothetical remnants known as quark stars. And if those exist, the behavior of time could become even more complex. The early universe, when time began. There is one place where time did not slow. It began. The early universe, just moments after the Big Bang, was so hot and dense that the four fundamental forces were unified. Gravity behaved differently. Space expanded faster than light during inflation, and time itself may have operated under entirely different rules. We do not yet have a full theory of quantum gravity, which means we do not fully understand time at the earliest moments of existence. But we know this. As the universe expanded, space-time cooled and stabilized. Time, as we experience it, emerged from those early conditions, which raises a profound question. If time had a beginning, could it have an end? The expanding universe and the fate of time. The universe is expanding, and not just expanding, accelerating, driven by something we call dark energy. If this acceleration continues indefinitely, galaxies will drift farther apart, stars will burn out, black holes will slowly evaporate over unimaginable timescales. Eventually, the universe could reach a state of maximum entropy, a heat death. In that distant era, change would slow, energy differences would vanish, and without change, time would lose its practical meaning. Because time is measured by change. If nothing changes, what does time represent? But that's not the strangest part. Some cosmological models suggest even more dramatic possibilities. A big rip, a cyclical universe, or something entirely unexpected, where time truly breaks. So where is the most dangerous place in the universe? It is not defined by temperature, or radiation, or distance. It is defined by where our understanding of time fails. At the singularity of a black hole, at the first fraction of a second after the Big Bang, at the far future where entropy flattens all change. These are not just extreme environments. They are boundaries of knowledge, places where physics reaches the edge of explanation. And yet, we continue to explore, because every time we measure a star orbiting Sagittarius A, every time we detect gravitational waves, every time we refine our understanding of spacetime, we get closer to answering the question, is time fundamental, or is it emergent? The most dangerous place in the universe may not destroy matter. It challenges reality itself, and perhaps that's what makes it powerful. If you've enjoyed exploring where time bends and nearly breaks, subscribing helps support more science-based documentaries like this, because the story of the universe is far from finished. And the next discovery may change how we understand time forever. If time can stretch, slow, and possibly even emerge from deeper physics, do you think it is a fundamental part of reality, or something created by the universe itself?